So, gentlemen, I want to welcome us to how to use the rational method. Rational method, you must have heard people talking about rational method. It is a default model, a default template for modeling stormwater and sewer. Now, this is the example where we'll be taking. This is this is layout. In this layout, you have catchment A. This catchment might be a district. It might be an estate. It might also be a state,
Please,
a local government.
can I record? Please allow me to record.
So in rational method, this is the layout. Now this is catchment A. This is catchment C. This is catchment E. This is catchment B. This is catchment D. The outfall is somewhere here. In other words, we are assuming that water from this catchment is not going anywhere outside these places. It will flow through, and then there's a river along here. So this is what we call the pour point, the outfall. So this is where the whole water is discharging. So here now, there are houses. I want to assume there are houses, just like I have demonstrated to us before in this material, like here. Okay, so you can see there are house connections connecting both for sewer and for stormwater. It depends on which of the pipe. Is it the pipe at the down or the pipe at the top they are going? The one at the top is the storm, the one at the bottom is the sewer. So this is how the connection is. So that line you are seeing is just like this pipe now going, passing through at the middle of the street. So this is that pipe. So the pipe goes from catchment A, it joins catchment B here, and then join catchment C, meets it here. Okay, what is flowing inside here can be storm, it can be sewer. It's the same thing. The difference is that sewer comes from houses, storm comes from the area. That's just the difference. So now, these are the catchment characteristics. This is the length of each catchment A, which is equivalent to also to conduit, conduit A, conduit B, conduit C. These are the conduits: conduit A, conduit C, conduit B, conduit E. Then this is not important. The beginning, the end, the beginning, the end, the beginning, the end, which is what your surveyor would give you, because it is with this divided by the length of the pipe will give you the slope. So if you look at this, you see that this minus this divided by this will give you the slope. And then this is the riparian catchment that is contingent on this pipe. So this conduit now is passing through catchment A, which has an area of 15.63. Catchment B has an area of 5.47. Catchment C has 14.06. Catchment C has 3.9. Catchment E has 14.83. So the whole catchment is 75. So all these catchments now, 1, 2, 3, 4, 5, 6, 7, 8. In total, they are about 75 hectares. Now, this is small, but in citywide design, that 75 hectares can be 750 hectares, can be 7,500 hectares. And then this catchment can be as big as possible. But that is just the same principle. Because if this is Abuja, it means that Wooper treatment plant is somewhere here. And this is Wuse, Jabi, Garki, Kado, Uye, Central Area, Asokoro, all of them going to Wooper treatment plant in phase 3. Yeah, you had me right, in phase 3 at Idu. So as the designer, you need to prepare a table like this, showing each area, the slope, the length of the pipe, and the conduit name passing through it. Now, the next thing you do, you now do your design. When you do your design, you now go back to the model and then model it. So in doing my design now, this is how I start. First of all, as I said, you do catchment characterization. Now let's start with the stormwater, for instance. In doing the stormwater, I'll ask myself, what is the constituent of this catchment? What area is green area? What area is street area? What area is garden area? What area is roof area? And then how about the others? Now, before I assume I attach a peak runoff coefficient to the total area, it is the weight mean average of the respective subcatchments, the characteristics of the small subcatchment within the bigger catchment that will give you the overall value of the catchment. So that's what's happening here. So the first catchment is the gardens. The gardens constitute 63% of the whole catchment, and their runoff coefficient is 0.1. That means only 10% of water that falls will constitute runoff. The streets, of course, when I say street, you should know that it's like asphaltic road. The whole street in the area, in each catchment, is about 12% of the total area. And the runoff coefficient is about 90%, 0.9. That means 90% of the water that falls on the road will go to the stormwater drain. It makes sense. It makes sense. Then the next one is roof. The 20% of the catchment is made up of roof. And the runoff coefficient of roof is 0.9%, 0.95%. That means 95% of the water that falls on aluminum zinc or Almaco zinc constitutes runoff. That's almost 100%, and which is true in real life. Then the last one, that those are not, I can't account, maybe garden, carports, interlocking area, sewer spots, playground, and so on and so forth. They are about 5%, and I'm giving them 20% as their contribution to runoff. So we are assuming a homogeneous condition. We're assuming that all these catchments, A, B, C, D, they have the same parameter. In other words, it's just the same. That means who say one and who says zone 1 and who says zone 2 are the same thing. That means Lekki and Aja are just the same thing. You know that kind of thing. So what is good for the goes is good for the gander. So that means that all of them, for the simplicity of design, let's just assume that all of them have the same catchment. Then the other parameters is that we are using a storm of 10 minutes. In other words, we are saying that if the rain won't, let it fall for 30 minutes or 1 hour. The first 10 minutes, the intensity at 10 minutes is what I'm using. And we're also assuming that the design is for a rural area. It's for a rural area that will influence your return period. And for the sewer line, we are assuming, because it's a rural area, we are assuming low density. We are assuming that there are no more than 100 persons per hectare, which means 10 persons per plot, per square meter, per 1,000 square meters, sorry. That's what it means. And when I mean 10 persons, that means like it's a 3-bedroom bungalow in every 1,000 square meters. Take note of that. Water consumption, still for the sewer, I'm assuming that the water that each person is consuming, this 100 persons per hectare is consuming, is about 130 liters per capita per day. And I'm using a peak factor. Now, some of us will say, what is a peak factor again, engineer? Well, peak factor is the factor you use to multiply water in water reticulation that gives you the maximum time when your system is under pressure, when your system is most required. So the peak factor normally varies between 1.3 to 2.6 or thereabout. Abuja, they used 2 to design Abuja. Abuja was designed on they used 2.3, sorry, the peak factor of 2.3 to design Abuja. They designed Abuja based on 100 liters per capita per day. But when they applied a peak factor of 2.3, they got about 230 liters per capita per day. So in Abuja, I've had many engineers saying that Abuja 230 was used to design Abuja. It is not true. What they used was 100, but they applied a peak factor of 2.3. Now, parasite water is about 0.1 per seconds per hectare, and pipe roughness is 1.5. That should tell you that we are using what type of pipe, concrete pipe, and not just concrete pipe that is not very smooth, that has a lot of roughness in it. That's why the value is about 1.5, which is on the high side anyway. That means you are losing about 1.5% for every 1 meter of water moved along that pipe. That's the layman's meaning. So this place is parameters I use. This is for sewer, for sewer, for sewer, for sewer, for sewer, and for stormwater. So here is for stormwater too. So after doing that, don't mind about this. The next thing is now, you now start calculation. Calculate your dry weather flow, that which is your sewer. So I'm not going to ask myself, because I'm not talking about houses or number of persons I'm designing for. I'm going to convert this factor to per hectare, because my value, they gave me 100 persons per hectare. So I'm going to convert and say what discharge is being produced per hectare. What discharge is coming per hectare. So here, to calculate my dry weather flow, I will say water demand times population difference, population equivalent, times my peak factor. This peak factor is just like safety factor. Just assume it's a safety factor. A safety factor that will take care of your losses. Let me go back to this place. These two now will take care of losses, run calculation, peak value. Peak value normally occurs when water is most needed. Let me not go into all that so I don't digress too much. So, but this is now the calculation, how you got your dry weather flow, which is the water flowing in the sewer, foul sewer line or sanitary sewer line, or which is the amount of wastewater. So, water demand per person is 130 per liter per day. Population equivalent is 100 persons per hectare. I convert it to seconds by dividing it by A6400. Then I multiply by my safety factor or my peak water demand factor, which is 2. Then I add infiltration water, which is the parasite water, or this is the water to take care of case of infiltration into my pipe, in case my pipe breaks or my pipe becomes permeable, or I didn't use PVC pipe, I went to use asbestos pipe, or I'm using a corroded ductile pipe. Good. Or I'm using a broken concrete pipe. Water will be infiltrating. So at the end of the day, I am getting 0.401 liters per seconds per hectare. Why is the value in per hectare? Because this 100 is in hectares. So by the time you do addition, scale conversion, you're going to end up in 0.1. So I want you to imagine 0.4 liters are coming in. 100 people are generating this 0.4 liters per hectare. So if I want to convert it to liter per seconds and go to my chart, all I need to do, ask myself now is, how many hectares am I designing for? So if I multiply this value now by the number of hectares, it will now give me the value in liter per seconds. And with my value in liter per seconds, I can go to my chart and get my pipe size. So you see, the value is being left at the hectares because we don't know how many hectares we are designing for. Okay? Because there are some, I know I'm designing for 75 hectares, but those 75 hectares are also discretized into small hectares also. Now, let's come to stormwater now. Let's come to stormwater. Somebody, go ahead. I want record. Safana, I've given you permission to record. Okay. Now, when you come to, sorry, let me just remind myself I'm recording. Yes, I'm recording. So now, if you come to stormwater now, what is the maximum runoff? That's what stormwater is interested in. What is the maximum runoff we are looking for? The maximum runoff is now the rain intensity times the impervious area. Give me the rain intensity, give me the area that's impervious, I'll get it. If you break it down, it also means the rain intensity times the total catchment times the peak factor. So these two now is just the same thing. It's either you write it this way or you write it this way. If you're writing it this way, you must multiply by the peak factor. So if I multiply this times this, it will give me the impervious area. So in getting your peak factor, how do you get your peak factor? Your peak factor is now the mean weight average of the small catchment area. Remember, here we assume that what is happening in A is happening in B, is happening in C. But if what is happening here is different from what is happening here, then my peak runoff factor will now be the average of what is happening here relative to the area, add it to what is multiply by what is happening here. The same way we do mean. There's what we call weighted average in modeling, in science, in engineering. Weighted average. Weighted average is that average that takes care of the standard deviation. Is that weighted average that it's not just the average of the whole, but the average relative to their constituency area, relative to their contribution to overall total. That's statistics. I won't go in there. So now, if you check all these things we did here now, if you calculate all these things, if you sum all this together and get the average, the mean weighted average, you get 0.37. So that's how they got 0.37. If you get the average of this, not the mean average, but the mean weighted average. And the weighted average means I'll multiply this by the area plus this by the area, this plus this by the area, divided by the total area. That's how we do mean weighted average. And that's how the formula goes this way. It is the coefficient of each one times their area divided by the total area. That will give you 0.37. So this 0.37 tells you that 37% of water that falls on this catchment is what will contribute to runoff. So later I will now multiply that at 37% by the total area to get the equivalent area that is contributing to runoff. That's what it means. So if you do this now, the next thing you ask yourself is, what duration and frequency do I use? The frequency and duration you use is now based on what you are designing for. Are you designing for flooding? Are you designing for surcharge? Or are you designing for just ordinary storm? Okay. So from there, you go and choose. Okay. If I'm choosing, based on this now, you will choose the duration and also choose the return period. So you choose the duration, you choose the return period. Now, this place just tells you how we came about the peak runoff. We came about the peak runoff by considering this is the percentage that's contributing to runoff. This is the amount of water that failed here. But the amount that is actually runoff, that 37% is actually this green one. Because the other percentage will infiltrate, the other percentage will wet, the other percentage will depress storage, the other percentage will drift, the other percentage will evapotranspirate. Then you now take care of the slope. What is the slope of the area based on this? Remember, our aim is to get Q. But to get Q, we need to get R and A. And to get R impervious, you need to get the total area and the catchment and the peak runoff. So this peak runoff, these are all the things that influences it. You must put them into consideration. So the runoff we got here is about 126 liters per hectare. Okay, so this 126 now, you now multiply by the area, it will give you the catchment. So here now, this is now the sizing of the sewage line. You choose your frequency, you estimate the time of flow, you choose your IDF to get your rain intensity, you calculate the wet area flowing, which is the water treatment plant. Then based on this, you now choose an adequate pipe diameter. And you say that pipe diameter depends on the discharge, the slope, and the roughness factor. I've said this before in passing. So there you go, you do this. There you also use a step. So after doing this one, you do also the calculated flow time, you compare the results, and then you go ahead. So this one is what we've gotten. Tomorrow we're going to do this and then put it in computer. This is the one we also model in the computer. This is what you see here. Then, so you do this so you can see. Tomorrow I'll explain this. Our time is fast spent. Tomorrow you now see how you write the area, you do the wastewater, you do the stormwater, and you do the wet water flow, all based on this. So this is all what we're going to be doing tomorrow. You do this, you fill a chart. There's a chart you fill in. Sometimes you consult chart to get the result. All this I'm going to show us, all of us. I'm going to show all of us this chart. I'll show us this tomorrow. So let me show you the chart. Let me show you the chart so you can study it. This is chart of fractional method. Or let me put it to PDF. Okay, now rational method. So in explaining rational method, let me just explain to us what rational method, how it works, because this is so important for tomorrow. When you come, you write the pipe sizes. Gentlemen, please, it's important that you print this chart tomorrow. I beg you, print this chart tomorrow, because tomorrow I expect every one of us to write something. You are going to write, bring a pen, bring a plain sheet, and you're going to write these titles. Then we'll be doing it and we'll be filling it. So, but to help you, if you can print this chart, in fact, if possible, you can print the whole of this rational method. I don't know how many slides it is. It's about 33 slides, but you don't have to print it each per slide. You can print it like 4 per slide. 4 per slide will give you like 10 pages or thereabout, or 8 pages. Please, let's print it. It's very important, so that it's not only by learning from computer. So now, what I want to show us now is this rational chart method. This rational chart is so important. Here, you put the pipe number, you put the beginning of the pipe, you put the end of the pipe, then you put the area that the pipe is representing, just like we have in that chart I showed you. Then after that, you multiply this area by the equivalent dry weather flow. Then after dry weather flow, you go to your chart and you design your chart, pipe chart. But if the person is a troublemaker, okay, and you want to combine both, that means you now get the peak runoff. So with this peak runoff here, which is in this second chart, I hope you can see my hand. Let me see if I can see marker. So in this second chart now, you see, this is now the runoff equivalent. So if you multiply this runoff equivalent, this peak runoff, by the area, it will give you the area impervious. This is area impervious. This is it. So if you multiply this by this, it will give you this. So this is actually the area, the main area contributing to runoff. This is it. And it's only gotten by multiplying the peak runoff by the total real area. Then the peak runoff, you now sum it together. You do compound summing. You sum it by the one coming before it. Then when you sum it together, you now estimate the travel time and make sure that the travel time does not exceed 600 seconds, which is equivalent to 10 minutes. Remember, you're using 10 minutes. You must make sure that the water in any of the water must flow into the drain in less than 10 minutes. That's what it means. And that's the standard. So here, you also accumulate the minutes. Then here you state the duration, the rainfall duration. This is the rainfall duration. So based on the rainfall duration and the time of flow, you go to the chart.
Apologies for interrupting.
Sorry?
Apologies for interrupting. There's a question.
Okay, go ahead, sir. No, you're not interrupting, sir.
So how do you just said something now? You said that your flow time in the drain should not be more than 10 minutes. The question that has been pondering through my head about the entire process of this tutorial, especially for the rational method, is how do you calculate your flow time in your longest tube drain? Because you remember that if you have your catchment area, you must first identify the longest rational path of flow from one end of the catchment to the outfall. You did not talk about how you get that time, how you get the time for your longest for your the catchment, the time of flow for one end to the other.
I'll tell you, sir. Very simple. What is the formula for velocity? Velocity is distance over time, isn't it?
Yes.
You assume you fix velocity. So you assume a velocity of, our velocity is between 0.5 and 5. Normally, how they taught us, you assume a velocity of 2, optimal velocity. You assume an optimal velocity.
Kumbasom.
Yeah, thank you. God bless you. It's Kumbasom. So you assume a velocity of 2. So if you assume a velocity of 2, that means distance becomes, and the distance now means the distance from the beginning to the end of where the water will flow out. Let me demonstrate it.
I understand. Go on. Go on.
Okay. The distance between this point and this point becomes your D.
That's the longest tree drill in this example.
Then just God bless you. Your longest part, just like critical part. Then you now divide it by the velocity, because velocity is distance over time. So if you cross multiply, your time goes up, velocity goes down. So it becomes distance over velocity will give you the time, travel time. So you now look at the travel time and make sure that the travel time does not exceed your rainfall duration, because rainfall is maximum when the travel time is equal to the rainfall duration. That's a good question. It's a technical question. Who asked that question?
Hamid.
It's like you're doing masters or so or something.
No.
Okay. You did water resources?
I work. It's my primary field actually.
Okay. That's a very technical question, honestly. Now,
another problem I have with this rational method is that all the things you've explained, at no point did we talk about the possibility of overflowing in the drain. I realized that all the examples you have given were that of pipes as your channel medium, but in Nigeria we don't use pipes.
It's the same,
gravity
sir.
Drains.
It's the same.
And there's a complication in that.
No, let me tell you something, sir. Pipe, when I say pipe, is the same. Open drain or underground drain. The difference is that the surface area must be the same. If you are using open channel, normally it's going to be a rectangular channel. The surface area will be length times breadth. In circular pipe, all you need to do is just to say pi r square or pi d square over 4. If it's trapezoidal, you say half area of parallel side times half. It's the same.
Can I explain why it's not the same?
Okay, go ahead, sir.
If I undersize an enclosed pipe,
good.
Parenthesis on a closed, overspill cannot occur. But if I undersize an open channel, there's an actual physical consequence, which is that the amount of water, the flow is greater than the capacity of the pipe. Water comes out of the pipe and backflow occurs, or water flows over, like it flows over. So a very good example that I can think of is something that happened last year in Lagos at Isheri North. So Isheri North is a flatland floodplain area where they are close to the Ogun River. Now, a lot of their drains are unfortunately undersized